I'll start this off by saying, I was asked to come here, and I'm glad to be here. For one thing, it's warmer in here than it is in the exhibit hall, and if anybody else is freezing, but I'm cold. But as I was watching Eric's presentation, I've been worried because I don't normally give these presentations, and my boss said, "Hey, you're going to be there, give this 20-minute talk. So what am I going to do it on?" And I have to just tell you off the first, my slides are not as nice and artsy as some of these others. But what I was thinking about is, we talk about AR and VR, and we don't really talk about where that data comes from. So reality capture, what is it? 3D documentation, product design, reverse engineering. We have to ask what size of part are we trying to capture, or what size of scene, how we're capturing it, and what paths we're taking to bring it down the path. So what do we need? So how big of a scene size are we going to capture? So I've got a couple examples here. I've got something very large, a parking garage that has probably 200 scans. We ran 3 scanners for about a 4-hour period of time to generate that. So millions and millions of points, but it's a very large data set. And then something smaller, is there a little, well, okay, up in the upper right is a gas tank that's been scanned with a smaller device like what I have outside. So we have to understand what our volume of measurement needs are, and we have to understand what kind of accuracies we need from the result. So method of capture is, when I started getting into doing this stuff at Faro, it never occurred to me that there are basically 2 different types of ways to measure. There's contact or non-contact. You're either going to touch something to measure the part, or you're going to use some sort of sensor to touch and measure the part. Contact measurement is very accurate, but it takes a long time to touch all of these parts. Going back to our garage example, a surveyor would go out with a total station and a rod, and it would take them hours and hours to complete that task. But it'd be very accurate. It also means we have to have access to all the things we're trying to touch. So think of something maybe like a cylinder head. There might be areas in there that you have to be able to get in and touch, and so it gets challenging at times. Non-contact can help solve some of those problems. It's faster, but it's not necessarily less accurate, or not necessarily as accurate as touch probing. We're basically measuring surfaces instead of discrete points, and also we have to maintain a field of view or a line of sight, similar to what we're talking about with contact capture. Kind of going along those lines, we have different ways to capture using non-contact photogrammetry. That's very popular these days. And then think about what we're doing with photogrammetry. It's basically we're measuring light. So light, as we open up our shutter, light's reflecting off a surface and coming to it. Well, we can do something similar if we project the light. Maybe we cause an interference pattern and we measure the response. So using light interferometry, so it's a lot more accurate. Or maybe we use a laser as a light source and let that be our way to measure the surface. So also, I forgot to give you the pretext. I'm kind of giving you there's more ways that we can measure, but I'm giving you these in the way that Faro thinks about measurement, because that's really what we do. And the next slide will kind of go to that. Also, we also have to think about our coordinate systems and alignments, whether we're in real world or CAD-based coordinate system. Real world is nothing but a coordinate system. There's probably 300 different coordinate systems that comprise the real world. Or it could be something very localized like a CAD datum that we're trying to match into. So in the world of Faro, we have various products, and this is just a sampling of them, and I've got another product that we're going to talk to at the end. How do we measure our parts? So we can go different volumes on the left side, from small volume to large volume, and then accuracies from left to right. So the tracker is a large volume, very accurate laser tracking device, and we can get into something similar with a contact arm, measuring arm that has a scanner on the bottom, and then our blue light interferometer, the Cobalt, is shown there. And then that garage I did was with our new Focus product. So that gives you kind of an idea of what types of products can be used to measure these parts. So, we collect this data. What do we do with it? Well, we have point cloud data that we have to turn into mesh, because really point clouds are just collected data. In terms of geometry, they're only locations. They can have attributes, like in the scanner the focus scanner example, it's XYZs, and then there's an RGB value that's associated with it, or maybe a reflectance value. There's really no geometry in terms of length or width. We can measure between points, but we can't really get any data off of those points. We can convert it to mesh, so we're just going to convert our point data, and a mesh is just 3 points in space connected with some type of a line, and there's three edges, vertices, and faces that are associated with each of those mesh, with a mesh. So example, so using my gas tank, if you look at the top left, that's points, and then down at the bottom right is mesh. So we've got the points that actually came from the actual device, and then we've converted that data. So it looks very much representative of what we captured in the real world. So kind of wrapping this part of it up, software workflow. We collect the data, either scanning or probing it, convert it to mesh. We can extract it to parametric type CAD using systems like 3D Systems DesignX. And then we can also visualize our scenes for asset creation using the example of our parking garage, if you're doing something like gaming or VFX. So these are kind of our workflows we're going to go through, and I have an example of maybe how we do a product design. So maybe we have a Toyota FJ that we want to put a new bumper on. So we've got our device, remember the arm? We can actually probe and scan points. So this is an example of how we've created a point cloud of scanning. And we've probed maybe attachment points, bolt hole locations, something we need very accurate locations on, so we can take that data as well. And then we can align it to a coordinate system. In this case, we're doing a CAD-based coordinate system with a simple 3-2-1 geometry, or 3-2-1 alignment. And then we can define sketch planes and extract data off of the mesh. So we're just going to create this geometry, and then do extrudes, do lofts, do any number of operations to get it into a CAD model. And in the end, so basically we're just tracing over. So we're just creating lines out of the mesh data, tracing over top of it, and then we can take those and actually create parts. So this is an example. So we can do solids or surfaces, really any type of data you're looking for. You see we can define things like radiator planes. Okay, so it's very CAD-based. And then we can also analyze. So since now we have a CAD model that we've created, we can go back to the mesh and do comparative analysis to see, hey, how did that fit? So it's a very handy tool for this reverse engineering product design cycle. We can then export this into SolidWorks too. So it's a very easy to use. Yeah, now we're in SolidWorks. So basically, if you saw, we got the exact same parts. We're in one software, the exact same parts in another. Okay, so when we get into this reality and virtuality, so I've talked a little bit about product design and how we look at it. I found this, and I'm glad I'm the first person, because I really don't feel like I'm in the right audience here. I feel like I'm maybe not as well versed in AR, VR, but I think, I saw this and it really struck me because, you've got the real environment and you've got the virtual environment, and we're all somewhere in between there. This continuum that is about where we are and what we're trying to do. And hopefully this product that I have from Faro, well, okay, we're going to talk a little bit about VR AR devices. So you can be totally immersed into the environment, going all the way on the right side of that continuum. It's very hardware intensive. You have to have something on to be able to virtually be in that environment. Or you can augment by projecting something into your reality. You can also augment your virtuality. So you can go both ways. You can augment your reality, augment your virtuality. But how do we get ourselves into that environment? Well, in the Faro, once again, we're in the Faro world because I'm going to show you the Faro product design, or Faro's virtual inspector tool. So basically, we are going to use QR codes to recall models and have that display on our device. And then somehow we have to take that device, since we've got this device in 3D space and we're not really aligned to anything, how do we get ourselves aligned to our part? Well, we can either do markerless, like if it's geocoded, so when we see it, it automatically is in the right position, or we can use markers to kind of pull ourselves into that alignment. So kind of going back to the very beginning when we talked about creating parts, we still have to have a coordinate system. We still have to have a coordinate system here. So what we're going to end up with is something that will allow us to be in reality, interact virtually with our parts. So the Virtual Inspect and Virtual Inspect AR. So we have two different products. They both run on an iPad. Here we're showing this in an environment on a tripod. And we basically, you have the QR codes or the digital codes that we see that when the photo recognizes that, it pulls up the part. It has a cloud-based attachment to it, so we can pull the part from the cloud, show it up on our iPad, be registered into that environment. So it can provide us with 3D data that we can visualize and highlight in our manufacturing insights. So looking at our typical industries and applications, we're very heavy like in the automotive and aerospace. I had somebody ask us if we're into the BIM sim world yet with architectural, and I'm sure it'll be there soon. It's just taking another CAD part and showing it into a reality. So you can see some of the different applications for this. If we have incoming goods, we want to do a quick check. If we're doing assembly, I was actually at GM and they showed me how they're using it with like a wiring harness as it gets installed in the chassis. The operator can just simply take their iPad, point it at it, pick up a couple of codes, and they can just visually walk with the iPad and just kind of look around to see if everything's laying in the right position. Assembly control and guidelines, 3D, quality assurance documentation, all of these things can be used with it. So the benefits, it's very mobile, it's very inexpensive, it runs on the iPad, so people pretty much have iPads, and we can save time and money by making it easy to use. You see here reducing scrap and rework, capturing, share, and real-time data quickly. So this is kind of an example showing it, what you would see on the iPad. Has touch functionality, so we can zoom in. We can actually take measurements on our parts as we see them. We can do quick comparisons, see if things look like they're lined up the way they're supposed to be. We can create cross-sections. As we look at it, we can actually see a cross-section in the field as we're standing there holding the device. And then we can add documentation. So say we're doing an inspection process or an inspection application, and we see something maybe is not the way it's supposed to be. So we can actually make a few notes inside of this and then export it out to an Excel spreadsheet. So the QR scan code, that's kind of the start of it. We just look at the QR code, take a picture, and then it pulls open the model for us. So now we have the AR version of this. So now we're going to augment our reality by projecting something into it. So in this case, you're seeing a fuselage of an aircraft that we can actually project maybe a wiring harness or some type of assembly that's supposed to be there. And we can visually see if it's in the right place. So once again, it's the same tool, it just has an extended use to it. We can see maybe if we're supposed to have some safety railing installed in an environment on the right, or if we're looking on the left model, just to kind of visually see if we're in the right place. Location independent overlay. We can take pictures on site, overlay our CAD data, take pictures at another time so we can actually document as we're moving along through our process. So how does this work? So we take inputs from different CAD models. You see STL, IGES, CATIA, from any of them. We compress them and create our own format, that MWPAK. So it's very lightweight. It can be thrown through the cloud very easily, and we can get it down to our device. I don't know, there's so much information on here. So we have a quick case study, and then I'm going to ask if you have questions on our products here. So this is an example of a European luxury vehicle and engine manufacturing company. Take 3 guesses. So they were able to use this in they found they have a very highly competitive marketplace, and they have very high standards. So they can take their QA process all across their manufacturing process. They can take this tool with them anywhere in their environment, and they can pull open the CAD model and visually inspect anywhere along the way.